Welcome back everyone to another video. In the last video we looked at number systems. We looked at general number systems, and specifically we looked at two important number systems. One is base 10 and the other is base 2. Base 10 numbers are what we as humans use, and base 2 or binary is of course what machines use. And it's important to understand the nature of both base 2 and base 10. We as humans use base 10, but when we move information into a machine, it's going to use base 2. It's going to use binary. And so to understand how base 10 and base 2 relate to each other is pretty important. So if you didn't get a chance to look at that last video, please go back. And actually there was two videos. There was a live stream where we went in and we kind of worked on the whiteboard and explained number systems, and then the PowerPoint kind of backed that lecture up. And it's good to watch both of those because I do talk about some things in the PowerPoint that I don't talk about in the live stream. So in this video we want to look at arithmetic. We want to look at specifically binary arithmetic. Inside of any digital device, any machine that can do math, there's a circuit, a special circuit called the arithmetic logic unit. And that circuit, or that arithmetic logic unit, is what enables devices to do math. And so we're going to consider just basic operations here: subtraction, addition, multiplication. We won't do division, but we could talk about division. But as you know, there's just four fundamental operations. I just listed the four fundamental operations: addition, subtraction, multiplication, and division. If you take out your calculator though and look at it, your calculator can do many more things. You can take a number and raise it to a power. You can, if you have a scientific calculator, some of the higher end calculators can actually do calculus functions like integration or differentiation. So we can do a lot with our calculators, but it's interesting to note that most mathematical things that you can do in your calculator can be broken down into the basic operations of addition, subtraction, multiplication, and division. And not only that, most or the basic operations here of division and multiplication can actually be done using addition and subtraction only. So for example, where you would take your calculator and you might go, I'm going to multiply 4 times 3. So you say 4 times 3 and you get 12 as a result. Well, the calculator can actually take 4 and add it up 3 times really quickly. Since computers move so fast, it could actually be adding instead of multiplying. It can add 4 3 times real quick and you think it multiplied it out, but it did that multiplication as an addition. And it's the same kind of thinking with subtraction and division. Division is just a fast way of doing subtraction. Well, if I want to divide, say I got 12, I want to divide it by 4. Well, I know as a result I'm gonna get 3. But what I can do is take 12 and subtract 4 from it. I get 8. So that 4 goes in at one time. I take 4 from the 8, I get another 4, so that's the second time. I take 4 from that 4, that's the third time, and then my result is a 0. So basically I've done a subtraction, but I did it in terms of division because that's faster. So division is just a shorthand way of doing subtraction. Multiplication is a shorthand way of doing addition. And so I can do those operations in the manner I just described, which means that the arithmetic logic unit, I can actually do everything with just what we call an adding and a subtraction circuit. And to go one step further, we can even do subtraction in terms of addition. So you know that if I take 7 minus 3, I get 4. I can also take 7 plus a negative 3 and I get the same result. So now I've narrowed my electronics down to just an adder. So we won't go into the details of that, but it's quite interesting to note that a lot of things that you do mathematically on your calculator can be done with a simple circuit called an adder. What we're going to do in this video to keep things simple, we're going to look at three cases. We're going to look at the case of binary addition, we're going to look at the case of binary subtraction, and we're going to look at the case of binary multiplication, and the subtraction is where the result is positive. Now, remember, this is all done electronically, so the idea here is just to kind of understand what the chips are doing. You can get an idea of what's going on inside of your digital device, be it a cell phone, PLC, or PC, whatever it is. First thing to do is to understand the rules. So there'll be rules for addition, rules for subtraction, and rules for multiplication. And if we were going to do division, honestly, division isn't difficult at all. We could actually do division. If you ask me about it, I could do some division on the board if you're interested. But there's basic rules. And here are the basic rules for addition. 0 plus 0 is 0. And remember, these are binary numbers, so I should say a binary 0 plus a binary 0 is a 0. This is true in any number system. A binary 1 plus a binary 0 is a binary 1. A 0 plus a 1 is a 1 in binary. And this one, a binary 1 and a binary 1 is actually a 1, 0, or we can say 0 carry 1. So remember, in the last video we talked about 8421 code. If I have a 1 here and a 0 here, and I convert that to decimal, the weight of this column here would be a 2. So a 1 and a 1 is a 1, 0, or 1 plus a 1 is a 2, if I think about it in decimal. So the first thing you want to do is understand these rules, the basic rules. And now we'll look at some examples. We'll apply these rules to some examples. Alright, so here on the left I have the base 10 representation of what I have over here in base 2. So if I think about the rules from that last slide, I have a 1 and a 0. Well, a 1 and a 0 is a 1. I have a 0 and a 1. From the rule, a 0 and a 1 is a 1. And then right here, I just bring the 1 down. So this is a binary 5. This is a binary 2. And if I add a binary 5 and binary 2, applying the rules, you see I get a 1, 1, 1, which if you convert that to decimal, you'll get 7. So you see that those rules actually do work. Now here's another one. I have a 0 and a 1. That's a 1. Here, I have a 1 and a 1. Remember that rule, when I have a 1 and a 1, the answer is 2, of course, but the way I write a 2 is a 1, 0. So what I have to do here is go 1 and 1 is a 0, carry 1. Just like when you add in regular addition, you have to carry. When you carry, you move it over to the next column. And so I got to do the same thing here with binary or any number system. I would have a carry. So a 1 and a 1 is a 0, carry 1. And then I add the carry to the 0. A 1 and the 0 is a 1. And then I just bring down that 1. So this is a decimal 10. A decimal 3 is a 13. Well, in binary, I have a 10. That's an 8 and that's a 2. If I use 8421 code, that's 10. This is 3. A 2 and a 1 is a 3. If I add it up, I get, if you convert this over using your 8421 code, you'll see that that is, in fact, 13. So make sure you understand this idea of a carry, how to use the carry. And in the live stream that you hopefully looked at before you watched this video, we've practiced that and you understand the idea of a carry. And here we go again. We're going to add 26 and 12. So I go 2 and 6 and get 8. I get 3 here. But here when I do it, I got 26 in binary. I got 12 in binary. Well, here I got a 0 and the 0 is a 0. A 0 and a 1 is a 1. A 0 and well, I said that wrong. A 1 and a 0 is a 1. A 0 and a 1 is a 1. But here I got that carry situation again. So I go a 1 and a 1 is a 0, carry 1. But in this case, since I have another 1 there, there's going to be another carry. So I got a 1 and a 1. I got the carry and this one. That's again, I write a 0 and I carry the 1, and then I just bring that 1 down. If you convert this over, 38 base 10, you should get this in binary. So those are some examples of addition. Subtraction is just as easy. Here are the rules for subtraction. Remember, these are all binary digits. So 0 minus 0 in binary is 0. A 1 minus a 1 in any number system, not just binary, is 0. A 1 minus 0 is, of course, a 1. Now look at this. This is a 1, 0. Remember, that's the way we represent 2 in binary. If I take a 2 and take 1 away from it, I'll have 1 left. So here I have a 1, 0, which is 2. I subtract a binary 1 from it, and my result is a binary 1. So take a look at these rules, and let's apply these to some basic examples. So I have a binary 3 and a binary 1. Of course, 3 minus 1 is 2 in base 10. Well, in base 2, I have a 1, 1 minus a 0, 1. If I apply the rules, a 1 minus a 1 is a 0, and a 1 minus a 0 is a 1. This number 1, 0 in binary represents 2 in base 10. So you can see that the basic rule works. Over here is another simple example. I have a 3 minus 2 is a 1. Well, here's 3 again in binary. Here's 2 in binary. So I go 1 minus 0, applying the rule. That's a 1. And of course, 1 minus 1 in any number system is a 0. So I get a binary 3 minus a binary 2. It's a binary 1. So again, the rule works. Now for this next one, we're going to look at borrowings. You have to borrow. Just like you do in base 10, you have to borrow sometimes. Well, here you have to do the same thing. So here we're going to take a 5, 3 in decimal. If I take 3 from 5, I get 2. Well, let's do it in binary. Here, applying the basic rule, 1 minus 1 is, of course, 0. But here's where I have to borrow. I go 0 minus 1. Well, we can't take 1 from 0. So what I do is I go next door. I got to borrow 1 from this leftmost column. So I'll take 1 away from here. And that 1 changes to a 0, but it comes over here as a 1, 0. That's important that you understand that step. So when I borrow 1 from here, it comes over as not a 1, but it comes over as a 1, 0, which is a 2. So now I can go a binary 2 minus 1 gives me a 1. Then I have the 0 minus 0, which is, of course, 0. So binary 5, take away binary 3, gives me a 2 in binary, just like in base 10. And again, this idea of borrowing is important. So if you don't understand the example here, please watch the video with the live stream. I'll explain this in greater detail, and I can draw on the board and show you more, and I think it'll be crystal clear for you. So there were examples here for addition and subtraction. They're pretty easy if you understand the rules. And let's look at this other interesting idea of another kind of subtraction called 2's complement subtraction. Now, you might remember in the last video and in the live stream, we talked about ways to represent negative numbers. And one way is to use a sign bit. We talked about that, the sign bit. The other way is to take the 1's complement. When you take the 1's complement, you just invert the bits. So that 1's complement is a form of a binary negative number. And then a third way of representing a negative number is the 2's complement. And that's actually the most important one for us. So the 2's complement is a form of a binary negative number. And so to take the 2's complement, just as a reminder, there's two ways to do it. You can take the 1's complement and add 1 to it, and that'll give you the 2's complement. But a quicker way to do it is to start from the rightmost binary digit, and you keep all the digits the same up to including the first one. Just leave those alone, write them down as they are, and then everything after that first one, you take the ones complement of it, so you would invert the bits. So again, I want to tell you to go back, and if you didn't get that, please look at that video, the video before this one, and we go over the ones complement and we go over the twos complement, so you should understand how to do that. Now, here I have a subtraction problem that you can actually do the way we've done in the previous slide. You can use direct subtraction, and then the live stream will do this using direct subtraction. So if you take a 1 1, now remember this is base 2, I'm not showing it here, but a 1 1 0 0 minus a 1 0 1 1, if you do the math, you borrow and all of that, you'll end up with 0 0 0 1. So you go ahead, you pause the video for a second, and what I would recommend is that you do this by direct subtraction, applying the rules we just looked at in the previous slide. Once you convince yourself that the math here is correct, we're now going to do the same thing using twos complement subtraction. Now, the way to think about twos complement subtraction, there's an analogy you can do in base 10. You can subtract using addition. I gave an example earlier where you can I could take 7 and subtract 4 from it and get 3. So that's direct subtraction. 7 minus 4 is 3. But I can also do that subtraction in terms of addition if I can represent the 4 as a negative number. So I can say I have 7 plus a negative 4, and that also gives me a 3. So I can do subtraction in terms of addition. Well, that's exactly what we're doing here if you understand that the twos complement of a binary number is just a way to represent that binary number as a negative number. So if I take the twos complement, making that number negative, the original number negative, and add it to the number, I don't know what you call I forget the name of the number, but if I add it, I'll end up getting the difference between the two. So again, try this using direct subtraction, and then what we're going to do is take the twos complement of this to get the negative of this, and we're going to add the negative to this original number, and it should give us the same result. If I take the twos complement of this, the way you do it is up to and including the first 1, I leave it alone. So the first digit is a 1, so over here I left the 1 alone. But after that first 1, every other digit you take the ones complement of it, which means you got to invert the bits. So here I have a 1, I change that over here to a 0. Here I have a 0, over here I change that to a 1, and here I have a 1, I change that to a 0. So here's the twos complement of it, of this original number. So now what I'm doing is I'm adding a negative. So I change this to addition, and hopefully you can see that of the methods that we looked at, addition is the easiest to do. So I can now add these up. I go a 0 and a 1 is of course a 1. A 0 and a 0 is a 0. A 1 and a 1 is a 0 carry 1. A 1 and a 1 is a 0 carry 1. So I get a carry out here. So I got 1 0 0 0 1. But I got this number in front. The carry that I had when I did the math in this column, I throw that away. Just when you do this twos complement method, you end up with a carry. Throw the carry away, and if you throw the carry away, you'll see that my result here and my result using direct subtraction are exactly the same. So that's earlier in the video when I mentioned that you can many of these operations can be carried out just with an adder. This is why you can do everything with an adder, because you can actually subtract. You can do a subtraction using an addition if you use a negative number, and for us the negative number would be twos complement. So make sure you study this slide and you're clear on how to do twos complement subtraction. There'll be a homework where you have to show that you can do this kind of subtraction, and then there's also a possibility that this could appear on a quiz or exam. So make sure you look at this, and if you have any questions, of course, let me know. I won't have much to say about this. You can read this on your own, but the yellow here, 2's complement subtraction has a clear advantage over direct subtraction. When implemented with logic circuits, subtraction can be done using only addition, so that an adder chip is all that is required. And if you guys want to explore that idea, it's kind of interesting. I know we're talking about some computer science here, topics in this course. So the fact that you can do all these operations using only an adder is quite interesting if you dig into the details of that. And I'll leave that to you to do that if you're interested. If you want to know more about it, you can ask me. I can actually show you how the logic circuit works. This is actually this adder and subtracting idea. This can actually be done using just our regular truth tables. I can show you how the circuits actually carry out these functions. So if you want to grind down into the details of this, send me a text and we can do a live stream, and maybe I can show you how some of this stuff works if you're interested. But we're going to move on to the final set of rules, and this is by far the easiest binary multiplication. So here are the 4 rules for binary multiplication. 0 times a 0 is a 0. A 0 times a 1 is a 0. 1 times a 1 is a 0. And I'm sorry, a 1 times a 0 is a 0. And a 1 times a 1 is a 1. Now, I can actually tell you a little bit about the logic of this. If you look at this, if you look at that, what does that remind you of? Now, we talked about truth tables, but we didn't use zeros and ones. We used true or false to represent switches that are open and or closed. Well, if you look at this, if you think of 0 as being false and a 1 as being true, then you can see that this would be, previously we used false, false, false. True, but I'm using 0, 0, 0, 1. This is your result for your AND function in the truth table. So binary multiplication is equivalent to ANDing. And I can show you that their other operations are equivalent to other basic truth table operations that we talked about. And you can see you can actually do this kind of stuff using logic. You can do multiplication using logic. You can do addition using logic. And since subtraction and division can be done using just an adder, you can do all of those using basic logic circuits. And so it gets to be kind of interesting, but we'll save that for another day. So if you understand these rules, and it's hard to go wrong with multiplication because everything's a 0 except for 1 times a 1. So if I apply these in base 10, 3 times a 1 is a 3. Well, a binary 3 and a binary 1, I'm going to get a 3 also. I go 1 times a 1, that's a 1 according to the rule. A 1 times a 1, that's a 1 according to a rule. So binary 3 times a binary 1 is a binary 3 as we expect. So it works for base 10, it works for base 2. Now this one where I have a 3 times a 3 is a 9. Well, it's the same here, but you got to be careful to shift over. Know how you add a 0 when you multiply? Well, here we just shift the bits over. So I'm going to go a 1 times a 1 is a 1. And this 1 times that 1 is a 1. But then when I multiply this, I got to make sure that the result I shifted over. So I go a 1 times a 1, that's this 1. I've shifted it over here to the left one place. And the 1 times a 1 is a 1. So now I'm going to add these just like you do in base 10. You can think of a 0 here if you want, but bring that 1 down. A 1 and a 1 is a 0 carry 1. And a 1 and a 1 is a 0 carry 1. And I bring down the carry, and I get a binary 3 times a binary 3 is a binary 9. So you can see that it actually works. So this gets to be kind of interesting and fun. Well, all of this, as I said, is done by, or can be done by a simple, I don't know if it's simple, but it can be done by a logic chip called an adder. So I can do all of these functions. I can do multiplication, division, subtraction, and of course addition using an adder. And this is just kind of a representation of an adder. So here I have on the left side of this chip, in electronics, usually inputs are shown on the left and outputs are shown on the right, just kind of in general. So here I have this box which represents a chip called an adder. So I'm showing my inputs on the left. So this takes two 4-bit numbers. We have input A and input B. Input A is a 4-bit number and input B is a 4-bit number. And here they're just showing you, this is that 8421 code. They're showing you here, this is my most significant bit and this is my most significant bit. So I can take a binary number here, maybe I have a shift register over here, parallel in, parallel out, or serial in, parallel out, and I move the binary number from the shift register to these lines, and then I have another shift register holding the second number. I move it to this line, and when I tell it to add, what I get out is I get out the result of that on the right in binary. So the point of this slide is to let you know there's an actual device that you can go to the, I don't know where you would go. You used to go to Radio Shack, but you can go to the electronics store, or you can go online. You can order an adder, but more typically adders are part of the CPU. They're part of the arithmetic logic unit, but you can get just an adder if you want to experiment with some of this stuff. Well, guys, that's it for this. Hopefully that was interesting to you. That showed you can actually do math in binary. You can actually do math in any number system, but binary is what's important for us because remember, that's machine language. Here it says students should now complete practice exercises, and I was looking for a sheet of practice exercises that I thought I might have had, and at this time I couldn't locate them. So I'm going to continue to look for some practice exercises for you to do. There is some homework. I'll give you homework, and in the homework there'll be an answer sheet so you can see if you're doing it right. Now, since I'm giving you the answer sheet for the homework, it's like the answer to some of the problems. I may have you do the homework first and then show you the answer sheet later, but the point is you want to practice this, and I think I would provide answers so you can see if you were doing it right. But either way, practice, and if I need to put up or find more practice problems, I'll do that. It's not a problem at all. So that ends this video. I'm going to record a second one, so hang on. There'll be 2 for today since we didn't use up all our time. And I will see you guys in the next video. Thank you.